Thanks very much. So we proceed with the session, and the next speaker is John Sean from the MetOffice, and he's going to explain us how they implement vertically distributed Canopy parameters in their model. Looking forward to that.
Right, thank you very much. Hi, yes, so quick word of introduction for those who don't know me. My name's John Shonk. I work at the UK MetOffice. There's a small group of us working on urban stuff based in Reading. That's me, Lewis and Humphrey. And this is a piece of work we've been doing in collaboration with other people at the MetOffice and some people at the University of Reading. So it's all about progress towards a vertically distributed urban canopy in the unified model. I'm going to start with two quick disclaimers. Firstly, following on from what we had in the previous seminar, this is also a bit of a preliminary work. It's a progress report, really, on how we're doing, so it's very much not finished. But we'll give you a bit of an update of where we are. Secondly, as well, this isn't particularly remote sensing. This is more modelling based, but hopefully at the end I'll link it through to my post tomorrow, which is more remote sensing. So hopefully that will all come together quite nicely. So a few words of motivation to kick us off. My slide is not advancing. There we go. Okay, so the MetOffice runs the unified model, or the UM. This is the model we use operationally at the MetOffice. Within that is the UM, I should say, actually is the atmosphere model. That's coupled to Joules, which is the surface model that we use. That's a tiled scheme, so it describes the land surface in as 9 different types of surface tile. One of those is the urban tile. And there's an urban scheme as well in there called Marusis, which further subdivides that tile into a rooftop tile and a canyon tile. So it's a canyon scheme. It assumes canyons align randomly in all directions. But there's a few things we want to at least we can work to improve in the model. So for a start, the coupling between the two is inherently fixed at the bottom level of the atmosphere. So it's between the surface and the bottom, that's where the fluxes interact. The downside of that is as we get to higher resolution, which there is a general push for at the moment, that bottom level tends to get lower and lower. So at the moment, when we're running 100 metre, 300 metre models, it's a couple of meters above the surface. And if we're trying to represent buildings, which are obviously usually a bit higher than 2 metres, you're starting to get a few issues creeping in there. So rather than coupling above the canopy, which is really what we want to do, you end up coupling within the canopy. The assumptions we use to calculate the interactions rely on this system of equations called Monod-Nabokov theory. They don't apply within the canyon, so we're not quite applying valid equations. And the further problem is, of course, buildings do have physical height. They typically, if you consider a 2 metre model level, 10-metre building will extend through several model levels. We want to try and represent that interaction a bit more realistically. So we have a grand plan to do this. It's not going to be a quick plan. There's a lot of work to do. We've identified 3 big elements of the challenge, which is to fix the drag, the scalar fluxes, and the radiative fluxes, and make them a bit more vertically distributed. There's sort of a bit of a schematic diagram of some of the thoughts that we might be using there. So this is obviously a big problem, so we've decided to start on one part of this problem, which was initially to work on the vertically distributing the drag. And that was a decision made with colleagues at the University of Reading. We made a big plan, and we decided to start with the drag. So our first step to dealing with the drag is dealing with this, with the coupling level being really, really low down. So what we actually want to do is we want to raise this coupling above the canopy, ideally to something called the blending height. So the blending height is it's a concept where if you've got a tiled surface, you've got different fluxes coming out of each tile, so out of your grass area, your urban area, your forest area. And as you go up through the atmosphere, these fluxes are all mixed up by turbulence until you get to a level where the fluxes are horizontally, or can be considered horizontally uniform. That level is the blending height. So the way the coupling works anyway, the surface feeds a single flux into the atmosphere. So in the model, that's a sort of artificially a blending height anyway. So we want to couple ideally at or above this blending height, and certainly not 2 meters up among the buildings and among the trees. So first thing we need is a way of diagnosing the blending height, because it's not a constant, it does vary up and down in unstable atmospheres or turbulent convective atmospheres. It's higher up. stable nocturnal atmospheres is much lower down. That's an equation at the top. Don't worry too much about what all the terms mean, but LB there is the blending height. It's not a particularly easy equation to handle. The blending height scattered quite a long way through it. However, if we express that in terms of variables that are available in the and the joules code, it actually collapses down to something, got a laser point here, haven't I? Something much easier on this side, where you can calculate the blending height in terms of the surface transfer coefficient, which is sort of everything in that bracket all lumped together rather conveniently, divided by k squared, or multiplied by k squared, whichever way around it is. And this horizontal inhomogeneity scale, which is something we need to determine, that's basically related to like the patch size. If you think of the urban surface as being alternating patches of large roughness, small roughness, that sort of thing, that's the patch, and that's related to this patch length that we're going to. And an important thing about this equation as well is it's stability dependent. So that psi m function you see at the top there, that is stability, because we want the blending height to respond to changing stability. So here's a method we've come up with to define the patch length. It's a sort of a threshold method. It's quite tricky to describe in the few minutes I have here, so I'm going to try and do my best as quickly as I can. So we've got a field of roughness length up there, and for we pick an individual point and we define a domain, a square domain around it of size LL. And we then use this function D here. This is a structure function. So this is a simple spatial correlation between two domains of equal size. So we start off correlating the domain with itself. Obviously that correlates perfectly, and in that case D is 0. We then take that domain and we shift it and compare it with a domain of different displacements to the side. Obviously as you do that, the decorrelation will increase. And then we normalize that gradient. Sorry, we calculate the gradient of that, then we normalize it, and we define the patch length to be when that gradient falls below 0.1. If you want a bit more detail on that, you can come, I'll talk to you about it afterwards if you want. But here's a simple test at the bottom on an idealized grid. So these are checkerboard pattern of long and short roughness lengths with 5 grid length checkerboard. And over a range of domain sizes, LL, you can see the method does return a reasonably consistent answer for 5 grid lengths. For that, is what you'd expect. So there are other methods out there that are more about integral approaches, which sort of average a bit more over the grid, but they're not so good at returning a single constant value, which is more what we want to determine the patch length. Okay, so here are some examples of that patch length calculation on real world situations. So this is some roughness data from the London area. So we've got central London at the bottom, going out to the rural edges of London at the top. Some typical patch lengths there shown for those 10 kilometre by 10 kilometre domains. So this plot here, the other plot here shows, so this is taking a large number of points scattered over the London area and calculating the patch length for different domain sizes around those points to get a more of an idea of the general situation of what the patch length should be over London. So in this case, you can see above a certain scale of domain, you start to level off at a reasonably constant answer to a typical length scale for London, which is about 700 metres. That's one way you could go about determining the patch length. Another, perhaps more brute force method is just calculate it point by point, create a whole map of it that looks something like this. This could then be fed into the model as an input. Downside of it perhaps is it may need a bit of refining because it's a bit sort of blocky at the moment, which will be related to the size of the domains that we use. But then again, it is representing fair features or realistic features. So if you look in the centre of London in the middle there, you can see the patch length is lower, which you might expect because there's a lot more variability in terms of building height, building roughness. Whereas that big blob, sort of northeast of London there, that's Epping Forest. So in the roughness length data we have, it's tall, but it's much smoother, so you've got a much bigger patch length, which again is what you might expect. So those are two ways of doing it. Either pick a single representative value or calculate a map. There is also the possibility we've not looked into yet of trying to find a sort of more empirical relationship between patch length and, say, some property like urban fraction, forest fraction, something like that, but that's something we're still thinking about. Okay, in the last few minutes, we have made a bit of progress as well with coding. So we have actually coded this up. We have raised the coupling level in the model, which is quite exciting. So the top row is what you get out of the model if you couple it at the surface as we do normally. So as you can see, the coupling level there is 1 everywhere, which is what you'd expect. And that's a diagnosed blending height using that equation in that case. So you get a set of blending heights with larger values over London, which again you might expect because it's rougher, up to about 160 metres. If we couple at the blending height, then that becomes a prognostic blending height, so it's feeding back into the model. You get a variation coupling level up to about model level 5, and the blending height about 10 times smaller, which there are reasons for that. I won't go into in detail. Maybe talk to me afterwards if you want to learn a bit more about that. A slight issue with this equation, though, is that it's not quite balanced. So technically, that CD term that we had neatly in the equation last time is actually dependent on the blending height itself. So when we're calculating the next step blending height using the current step transfer coefficient CD, we're actually using that at the previous blending height. So technically, that really needs to be a bit more iterative or a bit more implicit, but that's not actually particularly easy to do. A downside of this is that we do actually get oscillations in blending height. So where you're calculating one value from the next, we are actually seeing hops up and down. So at the top, this is a map comparing the blending height, the prognostic blending height at 3 consecutive time steps. If you compare step 18 to step 19, you can see it hops up. 19 to 20, it hops down, whereas 18 to 20 is about the same. If we pick an individual pixel out of one of those areas where this oscillation is the greatest, you can see in particularly the stable case, it is very, very unstable in terms of its fluctuations. So that's something we need to address. So a quick trip through the highlights. That's basically where I've got to at the moment. So yeah, work's underway on this vertically distributed scheme. We've got this horizontal homogeneity scale calculation, which we're in the process of developing, and we need to find out. I've got to shut up now, I'm afraid. So one final quick thing, I'll leave you to read that. If you want to see something a bit more related to remote sensing, come and see my poster tomorrow. It's all about comparing land surface temperatures out of the model with land surface retrieved from Landsat. So if you want to see something a bit more remote sensing, come and see my poster tomorrow. I'll leave that up for you to read. Thank you very much for listening.
Thanks very much. Well, it's a very interesting presentation.